Flow Assurance and Material Corrosion Study for Subsea Gas Pipeline, ensuring safe and efficient underwater pipeline operation. Study Overview and Objectives, Purpose, Scope, and Drivers of the study. This flow assurance and material corrosion study is conducted for a subsea gas pipeline to ensure safe, reliable, and efficient operation throughout its design life. The primary purpose of the study is to evaluate steady-state hydraulic behavior and internal corrosion risks under representative operating conditions, and to use these results to determine representative inspection locations along the pipeline. Flow assurance and corrosion are closely linked disciplines, as hydraulic conditions such as pressure, temperature, velocity, and liquid holdup directly influence corrosion mechanisms and rates. The study supports the pipeline integrity management philosophy by identifying potential operational constraints, degradation threats, and high-risk locations that require focused inspection and monitoring. From an operational perspective, the study aims to verify that the pipeline can meet required export rates while maintaining pressures and temperatures within design limits at both the departure and receiving facilities. This includes confirming compliance with landing pressure requirements and avoiding conditions that could lead to flow instability or excessive liquid accumulation. From an integrity perspective, the study provides quantitative inputs for corrosion rate prediction, enabling informed decisions on corrosion allowance, inspection intervals, and mitigation strategies. In accordance with international standards and recommended practices, an additional purpose of this study is to support risk-based inspection, RBI, and life cycle integrity management. Standards such as DNV STN 101, ISO 13623, and DNV RPF 101 emphasize the need for analytical assessments to identify credible threats, rank risks, and focus inspection resources on the most critical locations. By integrating hydraulic and corrosion analyses, the study also supports long-term planning for operability, maintenance, and potential life extension of the pipeline. Overall, the study forms a key technical basis for safe operation, regulatory compliance, and cost-effective integrity management over the full life cycle of the subsea gas pipeline. Steady-state hydraulic study, hydraulic modeling approach, and key outputs. The steady-state hydraulic study forms the foundation of the flow assurance assessment and provides critical inputs to the corrosion study. The analysis is performed using the Olga steady-state preprocessor, which is widely recognized for multi-phase flow simulation in subsea pipelines. The hydraulic model incorporates detailed pipeline design data, including internal diameter, wall thickness, roughness, and elevation profile derived from bathymetry. Environmental conditions such as seabed temperature and ambient pressure, along with defined production rates and fluid properties, are also included to ensure realistic representation of operating conditions. Boundary conditions for the simulations are typically defined from the outlet shutdown valve, SDV, of the departure facility to the inlet SDV of the receiving facility. Steady-state cases are developed for maximum gas, maximum liquid, and relevant design cases representing early, mid, and late life operation. These cases allow evaluation of the operating envelope across the expected range of production scenarios. Key outputs from the hydraulic study include pressure drop along the pipeline capacity curves, pressure, temperature, and velocity profiles, and arrival conditions at the receiving facility. The study also assesses liquid holdup under various production rates, which is critical for understanding potential liquid accumulation in low points and its impact on both operability and corrosion. Flow regime identification is used to evaluate the likelihood of severe slugging, which can pose risks to topside facilities and exacerbate internal corrosion due to intermittent liquid exposure. Overall, the steady-state hydraulic study verifies that the pipeline can operate within design limits, identifies potential flow assurance risks, and provides essential parameters such as temperature, pressure, and flow velocity for subsequent corrosion rate modeling. Flow assurance risks and implications. Identification of hydraulic and operational risks. Flow assurance risks in a long-distance subsea gas pipeline are primarily associated with multi-phase flow behavior, pressure and temperature variations, and liquid management. The steady-state hydraulic results are analyzed to identify areas where pressure drops may approach operational limits or where temperatures may fall close to hydrate formation thresholds. Although hydrate analysis is not the primary focus of this study, understanding temperature profiles is essential for overall operability and integrity considerations. Liquid holdup is a key risk factor, particularly in undulating seabed profiles where liquids may accumulate in low points. Such accumulation can reduce effective pipeline capacity, increase pressure losses, and create conditions favorable for internal corrosion. Flow regime analysis provides insight into whether stratified, slug, or annular flow is expected under different operating cases. Severe slugging, if indicated by the flow regime and pipeline geometry, can lead to large fluctuations in flow rate and pressure at the receiving facility, impacting process stability and equipment integrity. Fluid velocity profiles are also evaluated to ensure that velocities remain within acceptable limits to minimize erosion corrosion while still being sufficient to transport liquids and solids. Excessively low velocities can promote liquid dropout and corrosion, while excessively high velocities may increase erosion risk, especially in the presence of sand or other particulates. By systematically evaluating these flow assurance risks, the study provides a clear understanding of operational sensitivities and establishes a robust basis for corrosion assessment and integrity planning. Corrosion study methodology, internal corrosion assessment and modeling. The corrosion study focuses on assessing internal corrosion threats for a subsea gas pipeline constructed from carbon steel. The assessment begins with a comprehensive review of operating conditions and environmental data to identify credible corrosion mechanisms. Key input data include the design basis, gas and liquid compositions, produced water properties, and the presence of corrosion-related contaminants such as CO2, H2S, oxygen, chlorides, and solids like sand if applicable. Corrosion rate prediction is performed using ECE software, a widely used corrosion modeling tool for oil and gas applications. The model uses hydraulic outputs such as pressure, temperature, flow velocity, and liquid holdup to calculate expected corrosion rates along the pipeline. CO2 corrosion is typically the dominant mechanism in gas pipelines with free water, while H2S-related corrosion and erosion corrosion may also be relevant depending on fluid composition and flow conditions. The use of carbon steel as the base material aligns with common industry practice and applicable standards, but it requires careful assessment of corrosion allowance and mitigation measures. The corrosion modeling results identify locations with elevated corrosion rates, often associated with low points, areas of high liquid holdup, or changes in operating conditions. These results form a critical input to integrity management decisions, including inspection planning, corrosion monitoring, and evaluation of the adequacy of design corrosion allowances over the pipeline's intended service life. Inspection strategy and standards compliance, representative inspection locations and applicable standards. A key outcome of the integrated flow assurance and corrosion study is the identification of representative inspection locations along the subsea pipeline. These locations are selected based on predicted corrosion severity, hydraulic conditions, and pipeline geometry, with particular attention to low points, areas of liquid accumulation, and zones with significant changes in pressure, temperature, or flow regime. By focusing inspections on representative and high-risk locations, operators can achieve effective integrity assurance while optimizing inspection costs. International standards and recommended practices provide the framework for this approach. ISO 13623 and DNV-STN 101 emphasize the need for integrity assessments that consider both operational and environmental loads, as well as degradation mechanisms such as corrosion. DNV-RPF 101 provides guidance on corroded pipeline assessment and supports the use of analytical studies to demonstrate fitness for service. NACE MR 0175/ISO 15156 offers requirements for material selection and corrosion control in environments containing H2S. In addition to determining inspection locations, these standards highlight another important purpose of such studies: supporting risk-based inspection and life cycle integrity management. By quantifying risks and understanding degradation mechanisms, the operator can establish inspection intervals, monitoring strategies, and mitigation measures that are proportionate to risk. This supports safe operation, regulatory compliance, and potential life extension of the pipeline, ensuring that integrity is maintained throughout its operational life.